Okay, so here's part three. We just did parts one and two. And as a reminder, part one was finding the electric field both inside and outside a um, conducting sphere of some radius. And part two was finding the potential near a conducting sphere at some arbitrary point nearby, but also the potential of the sphere itself. So what the potential of the sphere is relative to infinity, or I guess potentially relative to ground, if you wanted to define ground as infinity. And now we're going to use the result from number two here in this problem in a kind of an interesting way, because there's some interesting and non-intuitive things going on here. And so let me set the problem up for you. So I have two spheres. They're both conducting spheres. They have different radii, and I connect them by a long, thin wire. And then I dump some charge into the system. So everything's conducting here. So the wire is conducting, both spheres are conducting. So the charge will just move around until it finds whatever orientation it needs for the electric field to be zero. So in equilibrium, the electric field will be zero everywhere in the system. So in equilibrium, E is zero everywhere here. And that's really important because what that means is that the potential of every point in the system will be the same. If E is zero everywhere here, then the potential is the same everywhere. So why is that? That's because potential difference is defined this way you're integrating an electric field along some path. But if you're integrating nothing along some path, then you just always get zero. So that means if we know that both of these spheres have the same potential, and the wire has the same potential too. What we're going to ask about here is what happens to the charge in the system? Where does it go? Which sphere has more charge? And which sphere has a higher charge distribution? These are kind of interesting questions to answer. Hold on a second. Wait, what's going on? Okay, sorry about that. So potential is the same everywhere in the system. So what can we do with that? We can use the result from number two. So part of this problem there's a few approximations that we're making in this problem. One is that the spheres are really far apart from each other. So even though they're connected by this wire, they're far enough apart from each other that we can still kind of treat them as though they were in their own system. And what that enables us to do is to write their potential as if these were isolated spheres in space, at least approximately. So we can write that the potential of sphere A is just equal to K times the charge on that sphere times the divided by the radius of that sphere. And the potential on sphere B is KQB over RB. These are different expressions for the potential of A and potential of B, but this whole argument about the potential being the same everywhere in the system is an argument that says that VA has to be equal to VB. The potential has to be the same. There's no electric field between those two spheres. The other argument that we're going to make here about the system is that the wire is thin. And all that means is that the wire really doesn't hold any charge, or not enough charge compared with how much charge is on each of these spheres. So we're kind of going to ignore how much charge is on the wire and just assume that all of the charge is on either the big sphere, sphere A, or the little sphere, sphere B. So let's see what happens. So the two questions we're going to ask here are, so this, scrolling down a little bit. So this fact here VA equals VB, that one right there. What consequence does that have for a couple of things? First, we want to know sort of what's the relative amount of charge on the two spheres. And we might pause here for a second to take a guess. So if you think about it, it kind of makes sense that there'd be more charge on the larger sphere, because what determines how much charge is on each sphere? Well, when you start having a lot of charge on a sphere, a bunch of extra like charges on the sphere, you start to get repulsive force. So you'd expect that there's some point at which you have so much charge on a sphere that you just can't push any more on to that sphere. No more charge wants to go into that sphere. But if the sphere is bigger, there's more space for that charge to spread out. So you might expect that if the sphere is larger, you can find more spots to fit additional charge before you kind of fill up the sphere. So that's kind of the working hypothesis here. And let's see if that works out. So if we use these expressions for VA and VB, so VA is KQA over RA, and VB is KQB over RB. Then we can cancel the K's, and that leads us to QA over RA is QB over RB, and then I can write this as a ratio of charges comparable to a ratio of radii. So that says QA over QB equals RA over RB. So in my drawing, RA is larger than RB. That means that this is greater than 1. That means that this must be greater than 1 too. And that suggests that QA is greater than QB. And the amount it's greater is just proportionate with how much bigger it is in terms of its radius. So if QA has double the radius of QB, then the charge will be twice as great on QA too. And that's consistent with the hypothesis. So a larger radius, or at least the qualitative hypothesis. So the larger the radius, the more charge you can fit onto the sphere. But what happens about the charge density? That's kind of a different question. I can also ask about the charge density. So let me scroll down a little bit. So the charge density on each sphere. So what's the relative charge density on each sphere? So on sphere A, the charge density on sphere A, sigma A, would be QA over 4 pi RA squared. And the charge density on sphere B would be the same thing, just with B's instead of A's. So QB over 4 pi RB squared. But we still know this, that VA equals VB. That still says that KQA over RA is equal to KQB over RB. So we really want to write the charge densities we want to write the charges in terms of the charge densities here. So let me do that. So this says that QA is equal to the charge density times 4 pi RA squared, and QB is the charge density times 4 pi RB squared. And if I plug into my expression right here, and I'll kind of move that below, I guess. So then K times, substituting for QA, sigma A, 4 pi RA squared over RA is equal to K times, substituting for QB, sigma B 4 pi RB squared over RB. So I can cancel a bunch of stuff here. I can cancel the Ks. I can cancel the 4 pi's. I can cancel one factor of each R. And that leads to an expression that looks like sigma A RA equals sigma B RB. And if I write this as a ratio again, then sigma A over sigma B equals RB over RA. That's kind of interesting because that's the opposite ratio of what we had before. Before, when we were looking at just charges up here, that suggests that the bigger the sphere, the more charge it holds, which is kind of consistent with what we thought. But if we're talking about charge density, this suggests that the bigger the sphere, the less charge density it has. So it's holding more charge, but it has less charge density. And that goes linearly with the radius of the sphere. So if the sphere A is double the radius of sphere B, for example, then sphere A would have half of the charge density, which is kind of non-intuitive. And because of the way I've drawn it, where sphere A is larger than sphere B, this suggests that the charge density on A is less than the charge density for B. That's kind of interesting. So in this situation where the potentials have to be different, or excuse me, where the potentials are the same on both spheres, then that implies that the charges have to be different and that the charge densities have to be different, but in opposite ways. And that's kind of odd. And maybe we could talk about any intuition you have about that result. The charge result seems more intuitive, to me at least, but the charge density result seems less intuitive. And I'm wondering what you make of that. Maybe we can talk about it when we meet again in class. And I will stop it there. So thanks everyone for watching, and I will see you soon. Bye.